In the next section, we'll look at a linear time, worst case linear time algorithm for suffix sorting. And I want to hype it up a bit again, or make you aware of it. It's the most complicated algorithm we'll see in this module, but it's very nice that each individual step is not complicated. It's one of those cases where coming up with this idea in the first place was really tricky, or it took people a long while. It's also one of the newest results we're seeing. This was published in 2000. I know some of the authors personally. This is all not that long and old, decades old results. This is closer to cutting edge research, but still very elementary in each individual step. But the algorithm accomplishes this feat that we somehow avoided so far. You have to somehow take a leap to do this in linear time. And maybe by the end of it, you'll say, hold on, where actually was the magic step that made this do something that people first believed wasn't possible? And I guess there will not be such a step. Every single step makes sense and is totally understandable. Anyways, it'll take us through today to get there. So let's start with a bit of an overview first. To make this algorithm clear, I have to introduce a helper definition, just because it's more convenient to formulate the algorithm for that helper result instead of the suffix array itself. So remember, L stands for leaves, because the suffix array really is the leaves of the suffix tree and sorted in left to right order. And what we'll introduce is the inverse suffix array. And it's essentially all that you need for the definition formally is in this line. It's the array that stores the inverse permutation. I didn't mention this so far. The suffix array always stores a permutation of the numbers 0 up to n. Just because the leaves in the suffix array are numbered by the starting indices, these are from 0 up to n. And the leaves come in some order, so it's some permutation. There's no duplicate numbers and there's no missing numbers. That's what that's supposed to mean. And this array R, the inverse suffix array, just stores the inverse permutation, which means if the rth entry in the L array is I, then the ith entry in the R array is R, with small and capital R's. Another way to express this, so remember from the definition of suffix array, this meant that if you look at the suffix starting at position I, then there's R suffixes that come earlier in the alphabetic order. Another way to say the same thing is Ti has rank R, starting at 0. That's how we defined it. And so you can interpret this R as the rank of a suffix. So here you give me the rank. In the leaf array, you tell me the index is the rank, the how manyth in sorted order do you want, and I'll tell you where it starts. For the R array, you tell me where the suffix starts, and I'll tell you its rank. Okay, it's the inverse of the two things. There's another way to memorize L and R. It's convenient that it comes down to the same convention, same letters. That's this picture here. And if you're more graphically inclined, maybe that's easier to keep in memory. And we'll use this picture a few times. So let me go through what it shows. We have our text. Then here, that just shows all the suffixes nicely aligned. So we have the suffix that starts at 0, 1, 2, all the way up through the last position. And there's nothing happened, right? This is trivial to produce. You just leave one more letter off at each point. Now, there's the R array showing here, which is for each suffix, it tells you its rank in the sorted order. On the right-hand side are the same suffixes, but this time sorted alphabetically. That's what suffix sorting produces. And then that also matches the leaf array, the suffix array, because these suffixes will appear in the suffix tree. The leaves will appear in that order. So here we have ordered the suffixes by their rank, the first, second, and so we're zeroth. If we start with 0, the zeroth suffix is always just the dollar because we defined that to be smaller than anything, and so on. And so the second meaning for these L and R could be R takes you to the right and L takes you to the left. If you have, if you know where your suffix starts, say I want this one, I know it starts at index 1, then R takes you to the right. It tells you you find it on the right at position 4. So you would go over here, and indeed there you find an anaban again, and vice versa. Okay? So this is not a complicated definition. I droned on about it for a bit because I want you to memorize it well, because we'll work back and forth between those two. It turns out that these algorithms to compute the suffix array are more conveniently formulated to compute R instead of L. But if you have this relation, you can compute one from the other quickly. So that's a simple for loop where you iterate through the positions and then you access the array with the result. So maybe a nice exercise to program that. But that takes linear time and is a simple, quick algorithm. So if we can compute R in linear time, we can compute L from it whenever we need it. To make double sure that you remember this stuff, let's go through some corner cases again. So this is not really a trick question. It is just double checking that the terms are clear. Okay, we had a phenomenal 88 votes for the attendance code. Let's see how many answers we get for this one. So both these options, L or R, stands for, it doesn't need to be exclusive. Like they don't need to they don't exclude each other. Okay, let's wait till 50. Oh, okay, there we are. Not much waiting needed. It's again a lot of answers. So in this case, almost all are correct. Let's just quickly go through them. So first of all, a few things are essentially just the definition. The suffix array lists the leaves of the suffix tree in left to right order. That is correct. That's one way to define it. So R does not have any direct relation with that order. It's the inverse permutation, so this is not true. It sounds like left and right, so be careful, but that would mean R is the mirror image of L, right? If you would swap everything around. That might also be useful. It turns out not to be useful here, so R is just something else. R lists the starting indices of suffixes in lexicographic order. That's the other way around. That's what L does, as you see below. That was the definition of the relation between the two, so not much more to say about that. And the mnemonics, I didn't want to throw anything in to confuse you, so these are all correct. You can take L to stand for the leaf array or for going left in that picture from earlier. And R can be the rank array or going right. So if you keep in mind that these are the directions of where we go, then that's the way to memorize it. Okay. So time for the actual algorithm. We'll go through in stages. So this is the high-level overview first. The algorithm is called DC3 or SKU. That stands for difference cover, because you can generalize the algorithm, but that's not relevant for us. It does something fairly peculiar. So first of all, it recursively computes a part of the answer, namely all the ranks that start at indices that are not a multiple of 3. Right? So we have indices 0, 1, 2, 3, blah, 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 blah. And those that start at 0 and at 3 and at 6, these are excluded. But all the others we compute recursively. So 2/3 of the answer is computed recursively. Okay, let's suppose that works. We'll use that recursively computed part of the answer to induce, so to derive from that, the other ranks. So the relative order of those that start at positions a multiple of 3. What I should say about these ranks, so this R12 and R3, these are only ranking relatively within their set of indices. So R12 tells you among all those that don't start at a multiple of 3, which is the first, second, third, and so on, it doesn't put this in relation to the total set of all suffixes. And similarly for R3. Of course, the final answer that we want is, in a way, the combination of these two, where we can, for every pair of indices, say which one comes earlier. Or we can determine the rank for every index in the entire set. And it turns out that you can do this with a merging step, which is not too dissimilar from the merge sort algorithm that we've had. But it will have a few extra tweaks to it. So that's the high-level thing. Solve 2/3 of the problem recursively. For the other third, we'll use a trick to get them cheaply from that. And then the overall result we also get cheaply from these two things. Now, let's first suppose all of that is done and solved. Why does that give us the required time? It's similar to what we've seen about the selection problem, finding an element by rank. There we had this, I was drawing this picture where you have 1, then you have 1/2, then you have a quarter, then you have an 1/8, and so on. So you have always enough. Maybe you remember this snake picture. That's a geometric sum. We have something similar here. If we assume that this step and this step takes linear time, the second and third step, then we by and large spend linear time on the first recursive call, the topmost one, for doing these two steps. But we recursively have their same cost in the recursive call on the first part, but only on 2/3 of the input. And so if you keep going like this, you always have a factor of 2/3. You can upper bound this by going all the way to infinity with that sum. And that sum turns out to be 3. So you upper bound the overall cost by 3 times the cost of these two steps, assuming that they take linear time in their input size, which is, I mean, we'll have to show how to do that. But if we can show that they're in linear time, then the overall algorithm also just takes linear time. So that's the easy part. The rest of the time we'll spend arguing how we can do this. And note that all the formulation here is for R. As I said before, it turns out to be more convenient to compute the rank array instead of the leaf array, but we can compute the suffix array from R when we're done. The first step is just recursing. So in a way, that's not the hardest part. Let's look at the second step. So the second step, again, remember, we've computed this R12, and now we want to get R3 out of it. So R12 is known. For every suffix whose starting index is among those numbers, not a multiple of 3, we know the rank. And we can, by comparing the ranks, we can in constant time decide which of these two suffixes comes earlier in alphabetic order. Now, for all the others, we don't know anything so far. And our task is you can reformulate the task to sort these suffixes in linear time. If we have their sorted order, if they're in a list in sorted order, we can produce the rank array from that by just iterating through. The thing that occurs first gets the rank 0, the second gets the rank 1, what's at position I gets rank I. So it's a sorting task, but a strange one because we have this weird extra information. Again, in general, you would not be able to sort in linear time under these circumstances. It's not one of those cases. It's only possible because we have this extra information. So suppose we would like to compare two suffixes. So one that starts at 0 and then another one that starts at 3. We can't just go character by character because that would definitely be too expensive. In the worst case, if the text is really strange, it could take linear time. But if I chop off the first character, then I have something that starts at position 1 and at position 4 in this case. And now, while 0 and 3 were multiples of 3, if I remove one thing, and so I increase the index by 1, that's not a multiple of 3 anymore. For sure not. So I can take T1 and T4, and those two I can compare in constant time because I can use their ranks from this R12 array. So I can actually use this to do comparisons in constant time. If I want to figure out whether T0 or T3 comes earlier in the alphabetic order, I explicitly compare the first character. Now, if that one's different, I already know which comes earlier, whatever character is earlier in the alphabet. But if they're the same, then I instead look at the suffixes that remain after that. And those two, I have already all information I need for that. So in a way, you can rewrite this. Instead of comparing the whole suffixes, you take the first character and then the rank of the remaining suffix. So you formulate these pairs. These are pairs of one character and one number. So those can be ordered in constant time. OK, that's the first trick. And to turn that into a sorting algorithm, all you really need is the counting sort algorithm from back then in Unit 3. So here's a concrete example that shows that how that works. So we have a slightly longer text. And to make life convenient, we're chopping off parts, multiples of 3. So it's convenient to add a few more dollars at the end to make sure that we always have enough characters to compare. Here are the suffixes that we would like to sort now. That's the ones that start at multiples of 3. And here are all the others, which we have recursively sorted. So here they are in sorted order. And here's their rank array. I don't know if it's big enough to read, but you can check at the slides if you want. Now, taking, I don't know if that's visible here. I've separated the first character of those suffixes. So if you take the first character and copy that down as a column, and all the rest of the suffixes you replace by the rank. So for example, here, Banana Bands, Banana Man, Bananas Man. So if I chop off H, I only have Anna Bands, Bananas Man. And Anna Bands, Bananas Man is here. It has rank 5. So that's why we get the 5 over here. That's the forming those pairs that I mentioned on the previous slide. And just visually, you see now, instead of sorting these long strings, you have these much smaller objects. And we can use radix sort, which means 2 rounds of counting sort. I can first sort by the first character with 1 round of counting sort, and then the second round on among all those with the same character, I sort by the numbers. That's one way to do it. And then you get all of these in sorted order. And from that, you can just read off the ranks. Right, this one, T21, gets rank 0. 18 is the next, it gets rank 1, and so on. Okay? And that's the result of this step. That's R0. It's the ranks of everything that starts at multiples of 3. And we overall take linear time for this, just because each of those steps, constructing that list, takes linear time by just accessing the rank array that we got from the recursion. And the 2 rounds of counting sort take linear time. So it's overall linear time so far. Let's now have a look at the third step. We have at this point, we have T0, and we have T12. So we know the relative order of all the suffixes that either start with multiples of 3 or not with multiples of 3. So these are like 2 sorted runs. You have a sorted list of strings, and you have another sorted list of strings. So in a way, what we can do is apply the standard merging algorithm from merge sort. And indeed, we'll do exactly that algorithm. What we need is a trick to speed up comparisons again. What would not work is at each point, I have to decide which one is smaller, the $1 or the $2. For those short strings, fine, it's a $1. But if you compare some long string, what you cannot do is go through character by character. That would give you a linear time for just one comparison. But we'll have to speed things up. Let's see. We saw a trick just before by splitting off the first character. And let's see how far that gets us. So let's suppose we have started the merging. So let's briefly simulate that. So we start at the first position. I'll take the smaller of the 2. That's this one. Put it to the output. Then I move 1 position down. This time this one wins. $2 is smaller than $3. Then this time that one wins. $1 is earlier than any other character. And now things start to get a little more interesting. Both starts with an A, but then H comes before N. So move that one down. And now we move this one out because A and dollar comes before A and A. So I sketched how you would do the character by character wise comparison just to get us to this point. But this is not what the algorithm would do. So the next step is to compare these two. The general situation where you could have some long strings. So let's try the same trick that worked for step 2. This is one from the green run. This is one from the blue run. If I remove the first character, what's left is some suffix from the blue group. So it's A followed by T16. If I do that with 11, it's also A followed by T12. But somehow the trick failed us in this case, because what we started with was 2 suffixes from opposite colors. And by removing a character, we got 2 new suffixes. They swapped roles, but they're still from opposite colors. So it didn't work in this case. But if you go one step further, if you remove a second character, then it always works. So in this case, if you take 16 and 12, and you chop off one more character on either side, you're guaranteed to get 2 blue ones. And this works in general because think about a general situation. So I have my 2 suffixes. I don't know exactly where they start, but they always have this pattern: 1 green character and then 2 blue. In the sense of, I'm coloring characters. If you start the suffix at this position, you would get a suffix of that color. Right, so this is a multiple of 3. And these two are not a multiple of 3. So if you just write the indices in modulo 3, you always get a 0, 1, 2, and the 1 and 2 are blue, and the 0 is green. Now there's different options how things could align, but suppose this one starts with green and then 2 blue. So I have green and blue. I cannot compare them directly, but if I remove one character, I have blue here and green here. Still doesn't work, as in this case. If I remove another character, then I'm back to both blue. The other option that you could have had was would have been here 2 blues. And in this case, one step is enough. If I remove the green here and the first blue, then I have 2 blues. And that's the only 2 cases you can have. You start with 2 opposite colors, so that one has to start with green. And then the one that starts with blue, it could either be a 1 or a 2 modulo 3 that you start with. And in both cases, either you remove one character or you remove 2 characters. After that, you have 2 suffixes that are both from the blue group. And so you know how to compare them. So what the outcome here is, I can use R12 to resolve any comparison after checking 1 or 2 characters up front. And so I can do every comparison in constant time. So maybe let me spell that out. So by checking whether your starting index of the 1 is modulo 3 a 1 or a 2, you can determine whether you have to check 1 or 2 characters. And if they're the same, then you have to compare what R12 gives you, but then you've resolved the comparison. If every comparison takes constant time, then the overall merging algorithm takes time linear in the size of the output. That's the same analysis as we've looked at in Unit 3. So with that, we could actually do the merging in linear time too.